In this video, we'll cover the problem number of islands. We'll be given an input, which is going to be a grid consisting of zeros and ones. We want to count the number of islands that are present in this grid. So the islands are defined based on these zeros and ones. So 0 is going to represent water, and 1 represents land. So an island is sort of a group of ones together that are separate from the water. We've actually seen this question before in the BFS question, or in the BFS section, but now we're going to solve it using a DFS because either is a totally valid solution here. So I'll go a little bit faster through explaining the question since we've seen it before, but I still do want to cover it because you probably don't remember all the details. So in this example, I will circle or outline the different islands. So this is one island, this is another island, and this is another island. So you can notice that we count ones to be connected going in the up, down, left, and right directions. But we do not count diagonal ones to be part of the same island. So in this scenario, we have a total of 3 islands. One thing that's important is you're usually DFSing through a graph. So one question here is like, how is this a graph? But as we've discussed previously, grids are often graphs in disguise because from a particular node, you can go up to another node, left to another node, down to another node, and right to another node. So we just call the elements of the grid our nodes. So the way we solve this question, as we've seen before, is we basically want to iterate through the entire grid and count the number of ones that we see. But for this entire island, we only want to count it once. We don't want to count it 5 times. So what we're going to do is when we see this one, we want to mark the entire island as visited so that we never visit it again. Previously, we did this using a BFS, or breadth first search. But now we're going to do it using a depth first search. So our high-level pseudocode is really going to be the same thing. So what we're going to do is we're going to iterate over our matrix and count ones. So iterate over our grid or matrix. I'll just say grid since that's what I've been saying. And we want to count our ones. What we want to do, though, is when we find a 1, so we'll say when, that's not clear, when we find a 1, mark the whole island that it's part of as visited. So we'll say mark its whole island as visited. That way, we will skip it in the future. So, as an example, we go through, let's say we have a counter over here. So we start off at 0. So we iterate through, we start at this spot, nothing, this spot, nothing. This spot's a 1, so we bump our counter. So we say, all right, we have 1. And then we say mark everything connected to this as visited. So we search up, down, left, and right. Up, left, and right don't go anywhere. But when we go down, we want to say this is visited. I'll put a V in the bottom left corner to say it's visited. So these 2 are visited. And then we continue searching from this one right here. So we go to the left. We mark that as visited, we go down, we go here. So all of these are marked as visited. Now we stop and we continue iterating. So we check the 0, it's not a 1, so we don't do anything. We get to this 1, so we bump our counter. So our counter says 2, and we mark this as visited. We can search all 4 directions, but there are no other ones, so it doesn't really matter. We continue iterating, we hit the 0, and we say we don't do anything. Now we hit this 1, but we see, hey, I've already visited this. Don't do anything, don't bump our counter, just keep going. We get here, we've already visited it, so we skip it, and so on. So the key idea is that once we realize that we have already visited a particular element or node, we don't visit it again. We've seen previously that there are really 2 ways with this kind of grid problem that we can track what's been visited. We can have, well actually there are a few ways, but the 2 ways we discussed are we can have a separate 2D array that contains booleans that says whether a corresponding location in the input grid has been visited. So as an example, our visited array at 2, 3, like this, is telling us whether row, so if we go 0, 1, 2, and then 0, 1, 2, 3, that's telling us whether this location has been visited. It's a Boolean that's going to be true or false. Or we can also just modify the input array. in some cases and say, when we visit something that's a 1, just flip it to a 0. Of course, when you do that, you want to check with your interviewer and make sure that it's okay to actually be modifying the input array. Sometimes they say it's fine, sometimes they say it's not. For the sake of example, I'm going to use the option where we store a separate visited grid, just to show you some diversity of what different solutions might look like. All right, that covers the general idea of how this algorithm works. Let's talk about the complexity of it. So, as always, we want to start by defining our variables. So we're going to say R is the number of rows in our input grid, and C is the number of columns in our input grid. These variables will allow us to talk about the complexity. So we want to analyze the time complexity and the space complexity. That's not very clear. Space. I'll rewrite it. Space. Okay, there we go. All right, so the time complexity is going to be O of R times C. And the space complexity is also going to be O of R times C. So let's discuss why. We know that we're iterating over every location in the grid. So that automatically means we're going to be O of R times C complexity. But at least the lower bound, like we cannot have any lower complexity than R times C. This part is certainly R times C right here. So the question becomes, what is this part? Well, we're basically traversing an entire island. So the sort of worst case scenario is if the entire matrix is full of 1s. We would hit this top left corner, and then we would mark the whole matrix as visited. So we traverse the entire graph, or the entire matrix, which is R times C, at once, just from this section right here. Oh, by the way, I should have mentioned, I'll just add a little asterisk. I'll say here, we're going to use a DFS to mark this whole section as visited. Anyway, back to what I was saying. So the DFS part does R times C work, or time. It takes R times C time in this worst case scenario where we have all 1s. Then we also do R times C work because we still iterate over the entire grid. So it's like 2 times R times C, which, we can drop the constant. So that's why the worst case scenario is R times C time complexity. Another way you can think about this is count the maximum number of times that we can touch any element. The maximum number of times we can touch any element is 2. If you remember our example, when we were here at this 1, let me remove that 0 pointer. We don't need to keep this. Let me just grab the eraser, get rid of that. Okay, when we were right here, we marked this as visited and then marked all of these as visited. So we just traversed all of these nodes here, we just traversed 1 time. Then later on, when we're iterating, we iterate here, we look at the 0, and then here, and now we've traversed this 1 for a second time. Only for a split second because we just check that it's visited and move on, but we, do some work on it 2 times. The first, when we found it through our DFS, the second through when we were iterating. It is impossible to touch this node more times than that because it's now been visited and we should never visit it again. So you can see that's another reason for why 2 times R times C is the upper bound. Every node can only be touched twice, and there's a maximum, well, not a maximum, there are R times C nodes. Okay, in terms of the space complexity, I mentioned that we're going to be tracking a visited grid that has the same size as the input grid. So our input grid is of size R times C, so our space complexity from the visited array is also R times C. If we were not using the visited array, our space complexity is going to come from the maximum size of our stack at any point in time. And I'm referring to the stack from the DFS. So in terms of how many elements that can have, we can DFS sort of going all the way up. So in this case, we could have 4 elements as the max on the stack, assuming they're all 1s. Or we could have 5 elements all in the stack, assuming they're all 1s if we're going to the right. So the space complexity in that case is you want to take the max of those 2 because you don't really know. You might have your DFS say, always prefer going to the right, and maybe this is a grid that is longest in the right to left direction, the horizontal direction. So the space complexity of the DFS in terms of how much space you use on the stack is going to be O of the max of R and C. But because we're choosing to do this using a visited matrix, that doesn't matter. That gets dwarfed by the fact that we have R times C right here. Okay, that's all for the approach. So let's go ahead and switch over to the implementation. All right, now let's see an example of how to solve this question in JavaScript. But before we do that, one note that I forgot to mention in the approach is that you might be wondering, like, okay, we can solve number of islands using a BFS or using a DFS, which one is better? And it really doesn't matter, because if you notice from the complexity, the time and space complexities are the same thing. So it's really a matter of preference. I would probably in an interview mention you can use BFS or DFS. The complexities are going to end up being the same thing. And ask the interviewer, do you have a preference on which one I use to implement it, or should I just go with my personal preference? And something like that. Normally, when there's multiple options, you should look at the complexity and pick the more efficient one. But in this case, it doesn't matter which one you use. All right, now let's see how we can go ahead and code the solution to this question. So the first thing I want to do is just create our visited array. So we're going to do create array of size. And we're going to pass number of rows and columns here. I'm going to store those in some variables. So we're going to say rows. Let's do num rows. It's going to be grid.length. And then num calls is going to be grid0.length. And so I should modify this to be num rows, and this should be num calls. One point that's important to make here is that num rows could potentially be 0, and then grid at 0.length doesn't make any sense, and that's problematic. So we'll do a quick check here and just say if num rows is equal to 0. Let's just go ahead and return right away. What do we want to return? We want to return 0 because there's no islands present. Okay, now we should write this function here, which is going to take a number of rows and a number of columns. And what we want to do is say const array is going to be a new array that has this many rows. And we want to just fill each position with num calls location. So we'll say, so long as I is less than array.length, I++. So just go through each position. And you want to say array at I equals a new array of num calls. So we're just creating a 2D array that has the same dimensions as an original array for our visited matrix here. And they're all going to be undefined, so falsy by default. And we can set them to be true if we want. We could also manually set them to be false. It doesn't really matter that much, so it's fine. I won't just for now. Okay, so now we've set up the boilerplate here. The way we want to do this is we want to iterate through every single position in the input grid or matrix. If it's a 1 and has not been visited, we bump our counter, otherwise we move on. And when we do find a 1 that has not been visited, we do bump our counter, but we also need to DFS through the whole island. So let's go ahead and iterate through the entire grid first. So we're going to say start our row variable at 0, go up through num rows and do row++. Same thing for columns. So we're going to do call equals 0, call is less than num columns, column++. And you can see I'm being careful with variable names. We're naming like row and call. We do num rows. Some people do like n and m for a number of rows and columns and stuff. It's not necessarily bad, but this is a lot more explicit and it's very clear exactly what you're doing. So it's my preference to do it this way. Okay. Now, what we want to say is if this position has been visited, go ahead and move on. If this position is a 0, go ahead and move on. So what we can say is, let's go ahead and grab the value just to make things simple. So we'll say current value is going to be grid at row at call. Yeah, that's okay. Grid at row at call. We want to say if the current value is 0, just continue. There's nothing to see here. If visited at row at call is true, we want to continue. Nothing to see here. But if we reach like line 33 and we have not continued, it means we have a 1 and it is not visited. So what that means is we need to add a new island. So we can create a variable here called num islands is going to be 0 to start. And let's make sure we return num islands at the end. Here we want to say, all right, we found a new island, so bump our counter. But we also need to DFS and basically mark the whole island as visited. So let's make a function for that. It'll be mark whole island as visited here. And it's going to take in some arguments, obviously. We'll figure those out in a second. All right, so what do we need access to? We definitely need the whole grid so we can look at various locations. We need the start row and start column, like Start row, start column. Yeah, that's fine. Like, where are we starting from? Start row and start column. We need this visited array because we want to modify it. And I believe that's all we're going to need. Yeah, we're going to need num rows and num columns. So I'm just going to grab this logic and paste it here. And we don't need this anymore because if num rows was 0, we would have already returned. Okay, now what we want to do, and this is where the real DFS logic comes into play, is we want to say, we found a new one, go through the whole island that's present here and mark everything as visited. So, actually, one thing I realized is, no, never mind, we don't need that. Okay, totally forget that. All right, what we want to do is use our DFS. So, we're going to say create a new stack, like this, and we want to push something onto the stack. The way we're going to do this is we're going to have every element on our stack be its own array that contains a row and a column. The reason is because we want to point to a specific location in our grid. And you can't do that using just one number. You need to have the row and the column. So that's why every element will contain a row and a column. All right, now we'll set up our standard stuff. So long as the length is greater than 0, you want to continue iterating. In the end, we don't need to return anything. All we're doing is modifying our visited array. Now, we want to grab out our current row and current column from the stack. So we can do it like this if we use some destructuring. If that is confusing to you, it is the same thing as doing like something like this. We can say the node is going to be stack.pop, so that gives us an array like this. And then we're just saying const row, or current row is equal to current node at 0, and const current column is equal to current node at 1. Lines 26 through 28 are identical to line 30. It's just cleaner syntax to do the same thing. It's totally fine to do it this way if you need to, but I'm going to do it this way just because it's shorter. All right, now we have the process node step. We'll come back to this in a minute, but let's go ahead and do the part where we add new nodes onto the queue. Sorry, not the queue, the stack. So since we're using a DFS, we use a stack. We want to push the positions that go up, down, left, and right. So we want to do cur row, cur column. Let's go up first. So if you're in a current position and you want to go up, that's saying go one row lower, like one less row. To go from like row 3 to go up, you want to go to row 2. So we do -1 there. Wait, what am I doing? Not there, sorry. Right here is where we want the -1. So this is going up. We can go down, which is going to be +1. Up, down. We want to go left. You can paste this. And we'll go left. To go left, you want to go, like, I guess I did it inverse, but from your perspective, you want to go left, which is this way. So if you're in a particular column, like column 3, you want to go to column 2. So you're going to do column -1. And we can do the opposite, which is going to be go to the right. It's going to be column +1. So if you're here, you want to go to the right. If you're in column 3, you should go to column 4 to go to the right. So we'll go +1. All right. Now we have the boilerplate of this function good to go. And there's nothing else we really need to do. Now we need to think, what are we supposed to do at each one of the ones that we hit? Well, the purpose of this function is to mark every single node within the island as visited. So let's just say every time we have like a current row and a current column, we want to mark them as visited. So we'll say visited at current row at current column equals true. We mark it and say, yes, we've visited this position. That's totally fine, but we also need some logic that's going to check some various conditions to make sure that everything is okay. As an example, if we're at a 0, we don't really want to be marking that as visited. It's not part of the island. It's also possible that we go out of bounds. You can imagine if we're at 0, 0, and then we try to go current row -1, we get -1, 0. That's invalid. So we should be careful about this. The very first thing we need to check is make sure we're in bounds. Because if we try to like check if a number is a 0, actually let me just do it and then I'll show afterwards. Or I'll show you once I put the other conditions. But the first thing is, let's make sure that our row and column are within the range. So if the row is less than 0, or the row is greater than or equal to the number of rows. If it's equal to the number of rows, that's still out of bounds. So greater than or equal to the number of rows, we should continue. Similarly, if the current column is less than 0 or the current column is greater than or equal to the number of columns, we should continue. So like skip if either of our row or column is out of bounds. Now, we also know that if a particular position has already been visited, we don't need to set it to visited and we don't want to continue searching. So we can say if visited at current row at current column is true, also continue, just go ahead and skip. And lastly is the case of if the current position is a 0, we can also stop. So we can say if grid at current row at current column is equal to a 0, go ahead and continue. We could also write this as not grid at current row at current column like this, because 0 is false in JavaScript, but I prefer this because I think it's a little more explicit. Now, what I was getting at earlier was that we cannot reorder the conditions. If we did it this way, that is not valid. To be clear, all I did is I moved these two conditions, line 35 and 36, which make sure that the row and column are in bounds. I just moved those at the bottom. But that is not okay, because if we had -1, 0 as our row, column, we would try to do grid at -1 at 0, and that's not going to work. We're going to have an error. So it's very important that these lines of code happen right here. The first thing we do is make sure that we have valid numbers. If we don't, we move on, we just skip. And we only do these checks on line 35 and 36 when we know for sure that we have valid rows and columns. Then, when we know that we have a valid number, it has not been visited, and it is not it is not a 0, meaning it's a 1, then we set it to visited and we continue searching. I believe that should be everything for this question. So let's go ahead and run it to make sure that it works, and then we can talk about the complexity. So let's see. The input we have is this one here, which is actually different from what we had before. Let's go ahead and switch it to what we had before, which I believe was this. So this was a 0, this was a 1, 0, 1, 1, 1. Yeah, I think this is what we had. So we have one island right here, another island right here, and another island right here. So the expected output is 3. Let's see what we get. It's running. Looks like we're doing dot length of undefined. So what is the issue? Which line had an error? Line 19. 19, where is that? Right here. Grid dot length. Oh, okay, yeah, I see. We're not passing any of the arguments to mark while island is visited. That's a typo. This is why I make sure that I test everything before we finish the video. So we need to pass grid, the row, the column, and the visited array. So grid, row, and column just come from our loop, and then we'll pass the visited array that we created on line 54. All right, now if we run it, we should get 3, I hope. Okay, great. We get 3 as our output, which is what we wanted. Now let's just write our complexity here. So we know that R is the number of rows in our grid, and C is the number of columns in our grid. So our time complexity is O of R times C. And our space complexity is O of R times C as well. For our time complexity, we discussed that we can touch every node at most 2 times, which means our time complexity would be O of 2 times R times C, which is just R times C. Or you can think of it as this loop certainly gives us R times C because we're iterating through every node, and our DFS in the worst case scenario will go through the whole graph 1 time, so that'd be 2 times R times C again. In terms of our space complexity, this visited array right here is going to be R times C space. You can see that right here. We're creating using R space right here, and then for each of those positions, we're using C space, so R times C. And if we weren't doing that, it would be the max of R and C, because we're thinking about what is the maximum amount of space that will be used on our stack at one point in time. And if we just went, up, then we could use like all of R space. And if we went left, we could get C space. Yeah, the number of columns space. So just the max of R and C would give you the space complexity there. All right, that's all for this video, and I'll see you in the next one.